Okay, so now we're going to be discussing about second order and higher differential equations. Now, there is a few problems with second order and higher differential equations. One idea is that there exists potentially an infinite number of solutions which could solve a second order differential equation or higher. So this then leads to the question, how do we even solve it in the first place? Well, it turns out that it doesn't matter if there's potentially an infinite number of solutions because we only care about two. So generally for a higher order differential equation, let's say an d to the n y divided by dtn plus a to the n minus 1 dn y n minus 1 divided by d to the tn minus 1, so on and so forth. The general solution, we only care about two parts, yc and yp. Now, yc is called your complementary solution. Sometimes it's also called the transient solutions or the natural solutions. In a system, this models a behavior of the system without any external interference. For example, if you kind of let an RLC network behave on its own in the absence of an external battery, then it will follow this natural response. For example, maybe decaying or growing faster. Now, YP is called your particular solution, or sometimes it's called your forced solution or external solution. These are solutions which are introduced by either the user, by a system, something that isn't necessarily part of a natural response of a system. So as such, we can take an infinite number of solutions and only care about these two, the complementary and the particular solution. Now first, the complementary solution is any kind of solution given by C1y1 plus C2y2 plus yada 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 Cn yn for an nth order differential equation. Now, this means that we have an n number of constants for an nth order differential equation. But we also have an n number of solutions to solve an nth order differential equation. So we do two things. We establish our constants. We also establish that we only care about as much solutions as the highest order of the differential equation. And as such, the complementary solution then, formally, as it's called, is made up of a linear combination of unique solutions. So just to kind of reiterate. So this is made up of an n number of unique solutions. This becomes important whenever you solve for a differential equation, a higher order differential equation, and you have to solve for a particular solution. You must make sure that the complementary and the particular solution don't overlap. Otherwise, the parts of the particular solution can get cut off, and we might not fully represent the system. Now, YP kind of depends on what kind of function you ask. If it's something polynomial, something exponential, something sine, cosine, then what ends up happening here, or rather, to be a little consistent, let's say this was instead x, or not x, t. To keep it a little, so to keep it a little consistent, if it contains one of four of these are easy to solve. These are easy to solve. If it contains combinations, maybe it's a little harder to solve. If it contains anything else, log, tangent, any kind of function that isn't continuous everywhere, then we have to solve it using a different kind of method, which will not be discussed here, but is simply just to show you that the particular solution really depends on what kind of right-hand side we are given. If we're given some kind of right-hand side where the particular solution is easy to figure out, then we can do so. However, later on, for the viewer, when you take any kind of differential equations, you may come across the superposition method, in which it is extremely hard to guess a solution, mainly because of this problem of YC needing to be composed of unique solutions. Or sometimes unique solution is a bit misleading. What I should say is linearly independent solutions. Or sometimes they're also called uncombinable solutions. So that is the idea behind complementary and particular solutions. We can have an infinite number of solutions to solve an nth order differential equation, but we only care about two, the complementary and the particular. In linear algebra, you might have seen this concept before. This is essentially representing a null space and a vector space. Next time, we're going to then be talking about how to, next time we're going to then be talking about higher order differential equations and ending with application. We could go on to talk about the different methods. However, the methods are really, really long. And for the viewer, it is encouraged that you will read through the material to try and understand the content a lot better. Thank you.